this morning, not so much about like a specific research paper of mine, but rather about that I'm seeing sort of over and over again, especially kind of in the Blockspace Allocation world, is what to talk about. And I've been having some really great conversations about this with Pranav Yaranidi and Mike Nutter, next to the audience. There's also a huge research post based on some of my thinking around this, if you're curious to read more. And as most of you know, I'm having sort of this in crypto, so I should say nothing about financial advice here, purely my academic capacity. Game theory is a funny field in the sense that it's like, on the one hand, it's a mathematical discipline. There's a lot of like deep theorems and stuff. On the other hand, arguably, its sort of most powerful and effective exports are things that are kind of mathematically trivial, like tiny examples, parables, I would call them. But you know, all of us, and even non-mathematical people, kind of see the world in a different way. The lens through which to recognize kind of many social issues, kind of examples, you know, more or less of these parables. There's a dilemma, most famous one, direct conflict between individual optimization, collaborative optimization, tragedy of the commons, variation of that same idea. If you don't know why there's a cow on this slide, go check out Harden's original 1968 article. Coordination, in fact, there can be multiple criteria, and there's sort of different ways you can coordinate on different ones, different equilibrium, better or worse, very important to all. Creates a paradox, and very hard. You give people extra options, the equilibrium can actually get worse. And I want to tell you about another one that I think makes for a good parable, which is a Tullock test. So with that, I'm not going to assume you ever heard of it. This isn't actually the most, the 1980 paper of Tullock that's most frequently cited about this. This is actually from a 1975 paper by Tullock, right? So before most of you, I thought it was going to be all before everybody in the audience was born. It might be before I was born. I have to check the publication month. I'm not actually sure. Anyway, 75. I'll let you read this. Those of you that have been following the theory closely in recent months may find some very similarities. So let me just give you like 20 seconds. So I know some of you aren't awake yet. So let me just part the equation for you. So it sets up this seemingly artificial game, right? Sort of two people, they can each buy lottery tickets for $1 each, as many as they want. The lottery ticket revenue you can think of as being burned, right? Not included, not added on to the product. So that's minus R minus player R, just loses all of the money they spend on lottery tickets. Player W, same thing. There's a prize. In this case, the prize has the same value for both D dollars. That's the D. Okay. The definition of the contest is the winner is whoever, you know, basically you win with probability proportional to the number of lottery tickets you buy. So one lottery ticket is sampled uniformly at random, and that's the winner. Hence the R over R plus W probability over here, and then the other probability within here. So for example, if R buys twice as many lottery tickets as W, they will win with 2/3 of. Okay. We'll come back to this. Right. So let me set this up now as a game in the sense of like Nash, right? The obvious generalization, we have multiple players. Okay. So I got to tell you the players, I got to tell you the strategy spaces, I got to tell you the payoffs. And then we have a game, we can start talking about equilibrium. Okay. Players, just the participants, each one vying. Oh, I should say. So what I'm going to do is I'm going to give you just sort of the basic definition, some foundations of Tullock contests. Then I'm going to show you 4 examples kind of the blockchain's Web3 world where these show up. Okay, that's the plan for the top. The foundations. So players are just the participants, they're all vying for this common prize. You can think about it about being a divisible prize that's sort of going to be split up amongst the participants, or as an indivisible prize which is going to be randomly allocated to one of the participants. But we assume risk neutrality, those are the equivalent models. Strategy space, you pick how many lottery tickets you buy. Okay, so you just submit a bid. Okay, in dollars, non-negative can be as high as you want. Okay. So what's the payoff? Focus on a strategy profile, because that's going to be the vector of the bids. Okay. Here's how your payoff is defined. It's all pay. And so no matter whether you have any chance of winning or not, you're going to pay for all your lottery tickets. They're non-refundable. And then you have a utility function, which is a function of however you want to think about it. The likelihood that you win the indivisible prize or the fraction of the divisible prize that you get. Okay, so that's xi. X is a number here between 0 and 1. Specifically, right, we had that R over R plus W and W over R plus W. It's going to be proportional. If you like to think about a lottery ticket sampled uniformly at random. So XI is just going to be your share of the overall investments for all the participants. Your bid divided by the sum of all the bids. That's your XI. Okay. And that's your payoff function in a Tullock contest. Okay. Your utility for the allocation that you get minus the investment that you put in. Okay. You might want to think about capital U as just being linear, okay, with some coefficient of u sub I, but everything holds if u is an arbitrary your concave function. Okay. All right, so when you teach these game theory parables, it's always important to sort of emphasize what are their features that you should be on the lookout for kind of in the wild, right? What in the wild should sort of trigger a thought, an instinct that maybe that's the parable that's appropriate. Two I want to highlight here for Tullock contests. So first of all pay. Okay? Even if xi is 0, you're still going to pay. Okay? So that's an interesting aspect of it. Obviously, we know mechanisms that are not of this form. Secondly, proportional allocation. That's really important. We also know mechanisms not of this form, right? Just like a first price or a second price auction satisfies neither of these two. This is sort of a different way of allocating something than say a first price or second price auction, as we know, I'm not big about it. Other ways to get a feel for it. So from an individual's perspective, there's diminishing returns of buying more and more lottery tickets. Okay, that's sort of obvious if U is concave, right? But even if U is linear, okay, even then there's diminishing returns of buying more and more tickets. Like imagine you're competing with one person, they've bought 10 tickets. Okay? The first 10 tickets you buy increases your winning probability from 0 to 50%. The next 10 tickets you buy raises it from 50 to 67. The next 10 from 67 to 75, and so on. Okay? The proportional allocation means even if you have a linear utility function, as far as your payoff function, that's concave. It diminishing ROI on further tickets. Okay? And so that gives you a lot of economic structure. So a special case is just where everyone has the same utility function, not that interesting mathematically. As you'd expect, you just get the symmetric equilibrium. Everybody bids the same, everybody gets their fair share, their 1 over n share of the object. So what's mostly going to be interesting for us is when people, for whatever reason, have heterogeneous utility functions. All right, so I'm talking about another old idea, the idea of potential games. I guess they only got their name in 1996, but really they were kind of already there when congestion games were defined by Richard Rosendahl back in 1973, so before even Tullock's work. Tullock was unaware of this potential game stuff. But this is a way you can understand equilibrium. I told you the game, now I want to talk about what the equilibria look like. And the idea in the potential game approach is to characterize the equilibria of a game as the optimizers, the global optimizers of some kind of potential function. Okay? So this idea was crucial in my PhD work on self-shrouding. This was very much in the air at the beginning of the century. And it was Johari and Sousiklis not long after, 2004. They weren't aware of Tullock contests, it seems like. Tullock was interested in kind of applications sort of in political economy, like lobbying and that kind of stuff. Johari and Sousiklis, they were sort of electrical engineers, so they were interested in sort of network bandwidth allocation. So they didn't know about Tullock contests, they kind of redeveloped that from scratch. They did know about the potential game formulation, which was in the air at that time, and recognized that the equilibria of Tullock contests can indeed be characterized as global optimizers, a suitable function. Let me show you that function now. Okay. So remember, strategies in the Tullock contest are bids, okay? But bids give rise to an allocation, proportional allocation. So this theorem characterizes what allocations can arise at equilibrium in a Tullock contest. Okay. So we're talking about objects that are just points in the simplex. Okay, so non-negative vectors that sum to 1. The probabilities, if you like, of winning for everybody involved. And so the assertion is that the equilibrium allocations are precisely the global maximizers of the sum of these, I'll call them modified utility functions, these U tildes. The U tildes are related in a simple way to the U's. So if the U's are degree D polynomials, the U tildes are going to be degree D plus 1 polynomials. One way to think about them is this is just going to be a weighted average of the actual utility function and the average utility up to that point. Okay, that's another way to think about these utilities. Details aren't important for us today. Not hard to prove this. Basically, you just make up the utilities so that the first order optimality conditions, so optimization problem, match the first order conditions for the best response mechanism of the game. And you discover you can do guess and check. This turns out to work. Okay. So that's pretty cool. Okay, analyzing equilibria of games in general is really messy, really hard. When you have a potential function, especially a concave potential function like this one, life is really good. Guaranteed existence of a unique equilibrium. And that's because this is a strictly convex optimization problem over a compact setting. Okay. Very unusual to have classes of games with guaranteed existence and uniqueness. Whenever you see that combo, it's usually for this reason. It's usually because there's a convex or concave potential function behind the scenes. Okay. So that's great. So Tullock contests, at least sort of in the full information setting with respect to pure Nash equilibria, we really have powerful tools for thinking about what they look like. Okay, that's gonna be useful later. So that's the foundation for Tullock contests I wanted to tell you about. So if you didn't know Tullock contests, now you do. If you've never heard of potential games, now you have. Seems like very few people have recognized the potential Tullock contests are potential games. So that's a simple but just powerful thing to know. Now I want to tell you about many places I'm seeing these Tullock contests around. Okay. Let me start with work of Nick Arnosti and Matt Weinberg, who are interested in possible centralization forces in Bitcoin mining. So Arnosti and Weinberg, they did recognize the connection to Tullock contests, and they built on that literature. They didn't use the potential function formulation. We'll use that in a second example. So they're just thinking about miners investing in hash rate. So miners who have to pay fixed costs, have to pay sort of electrical costs. Miners pay money, they get back in return. Remember what I said with the two key features of Tullock contests to be on the lookout for: the all-pay nature and the proportional allocation. So here's your all-pay right away. Okay? As a miner, you invest, you get hash rate back, doesn't guarantee you anything. You may or may not mine any blocks in the future, but you pay that cost no matter what. That's the all-pay aspects. Arnosti and Weinberg thought about the case where the prize was the same for everybody, the same way that D was the same for both people in Tullock's example. Pretty reasonable assumption in Bitcoin, where the block rewards tend to dwarf both transaction fees and MEV. And then, just assuming SHA-256 really is a random oracle, then in fact, just kind of, just from that assumption, you get that it's a proportional allocation. The probability you were the miner winning the next block is proportional to your hash rate. That's the second checkbox for Tullock contest. So this must be a Tullock contest. And it is. Now, from what I've said so far, it's just the symmetric case, right? Nothing is different for different miners. So you just have the kind of equal split, kind of the boring special case. So Arnosti and Weinberg said, well, what if some miners have cheaper access to hash rate than others? Either they have cheaper access to capital, or they have just sort of cheaper access to electricity because of where they're located. Does that have a centralizing effect on the equilibrium sort of investments, on the sort of distribution of mining power? And they were really kind of focused on negative results, I would say. So the math, in some sense, of the model in this example, the next example are exactly the same. They were more focused on a cautionary tale. So they were saying, look, if you have substantial heterogeneity in the costs, okay, so if some miners can get access to hash rate much cheaper than others, you're going to have a problem. So you might think they're like, oh, proportional allocation. If you have 10,000 miners participating, they all have a non-zero chance of getting it. That seems very decentralized. But they point out that, like, if hash rate is expensive to acquire for 9,900 of those miners compared to the top, so 100, they're just going to exit. Okay, so they're just actually going to sort of give up. You're going to be left with 100 miners who might have a large fraction of the hash rate. Okay. So if some miners can get it much more cheaper than others, you wind up with a sort of oligopoly type equilibrium. Yeah, that's what they show. All right, so table 2, this is in joint work with Miriam Barani and Pranav Giramidi. When instead of proof of work layer 1s, we wanted to think about proof of stake layer 1s, and we wanted to think about MEV specifically. Okay. So here, instead of miners, we're now talking about sort of participants in a proof of stake protocol. Okay, so think about someone who sort of locks up a bunch of stake and sort of operates validators, participates in the protocol. Think of those as sort of the same entity for simplicity today. The cost may not be as high as doing mining, but they're not zero, right? You're locking up capital, there's opportunity to cost. There's smart contract risks, right? You sort of have to operate the machines to participate in the consensus protocol. So there's some non-zero cost involved. But here, unlike the previous example, the value of the prize we wanted to model as variable. By thinking about Ethereum, it's not reasonable to just say block rewards dwarf everything else. You really have to take into account certainly MEV, maybe transaction fees and priority fees as well. Okay, so the prize is now going to be for sort of getting to produce the next block, the sum of all of the revenue streams you're accustomed to from, say, blocks in Ethereum. Okay. Again, just by the way the proof of stake works, probability of winning is proportional to the amount of stake. So again, we check the 2 boxes for Tullock contests. It's all pay. Just because you've locked up capital doesn't guarantee block production. And then here the same thing, just sort of by the way that it works, it's going to be proportional allocation. Okay, so you must have Tullock contests. And while Arnosti and Weinberg were interested in heterogeneous costs across miners, for simplicity, for today, for the talk, let's just assume everybody, all the players have the same capital and operating costs. You can generalize that too. Don't worry about it. And instead, we wanted to focus on the fact that some participants are more sophisticated than others. In the sense, they're in a position to extract more, say, MEV from a block than others. Lots of reasons why that might be true. They might have access to sort of their own sort of private stream of transactions. They might have spent a lot of money sort of putting together some proprietary, really good block building algorithm. Who knows? But like this is sort of a basically well-accepted fact about the Ethereum block building ecosystem, that some people are in a position to put together much more valuable blocks than others. We wanted that to be explicit in our model. And that Tullock formalism basically applies directly, right? We're really just literally on the Tullock contest, where the stakers, participants have linear utility functions, so VI times XI, where the VIs are different for different validators I. And so a higher coefficient, a higher VI, indicates a better ability to extract MEV from a block production opportunity. Okay? And in particular, we wanted to, in this paper, we did this in a few different ways, but one of the ways we approached this goal of assessing proposer-builder separation, articulating its goals, and understanding or sort of interrogating whether or not it actually achieves those goals, is we said, well, look, the point of proposer-builder separation is to kind of level the playing field, right? So like, if nothing else now, even if you're just a solo staker, you've got this backup option of just like using MEV boost, right? So maybe you suck at putting together valuable blocks, but there's this sort of, pretty small specialized sort of market of builders who are pretty good at it and offer you the ability to take their best block, the block with the highest bid, and use that in your place. Okay. And so if you posit, okay, there's other parts of the paper that actually try to prove that PBS does indeed make things relatively homogeneous across validators. Here, if you take that on faith, if you take it on faith that PBS is achieving the goal, right, that no one validator is like much better at extracting, given the existence of the builder ecosystem, no one validator is much better than anyone else at getting a reward out of the block production opportunity. Then you wind up in this exact same Tullock contest model, but unlike Arnowski and Weinberg, who focused on cautionary tales, negative results, we were focused on positive results. Okay, and so we wanted to say, suppose there's not too much heterogeneity, is it at least the case in this model that you are regionally decentralized among the validators, in the sense that no one staker is going to, at equilibrium, control a huge portion of the stake? And so the answer is yes. And so the main result in this part of the paper is we parameterize it by the competitiveness of sort of the block producer set. Okay. So there's two parameters, gamma and K. Gamma is going to be 1 or less. The closer to 1, the better. The bigger K is, the better, as far as being competitive. Okay. So if you had, for example, so maybe you have sort of one block producer who's kind of really good at extracting MEV. They can even do better than MEV boost some of the time, like 10% better than MEV boost. Then you have 10 other people that are just using MEV boost, so they're at least getting 90% of what the really good block producer is getting. So that would correspond to K equals 10, gamma equals 0.9. You want K people other than the best block producer to get at least a gamma fraction on average out of each block production opportunity as the best one. Okay, that's what gamma K competitive means. And using that potential function, that potential game formulation that I showed you a few slides ago, you can get an exact characterization of the worst case, meaning the maximum market share that a staker might have in a gamma K competitive ecosystem. Okay. So for example, if gamma equals 1, so that would actually say you have K plus 1 block producers all equally really good at extracting it. You get what you think you'd get, which is that they would basically just sort of, those K plus 1 block producers would just split. Okay, they'd each stake a 1/k proportion of the overall stake. And so this shows that as gamma drops below 1, it shows you exactly the sort of degradation, right? So look, if gamma was 0.9 instead of 1, and K was 10, okay, you might have sort of block producers, like the best block producer, it's not going to have nearly 9% of the stake, it might have something like 19% of the stake at equilibrium. Okay. And these are tight bounds. Okay, so the potential function formulation gives you kind of all the tools you need to exactly ask this question: as a function of the efficacy of PBS, what is the resulting decentralization? Okay, as measured by effectiveness of PBS, that's measured by gamma and K. Decentralization is measured by this maximum market share. And you're able to answer that completely precisely because of the tools you have around color. Okay. So I want to do 2 more examples. These are different than the last two. The last two, since we're really just talking about like layer 1 Sybil resistant block production, even if you didn't care about proportional allocation or all K per se, you wind up getting there just because of the other design constraints. Okay. So basically, you can even prove that if you want a way of allocating rewards, so say you have a layer 1 blockchain protocol that generates a reward per block, you want to allocate those rewards across the participants in a way which is Sybil proof and collusion proof. Then in fact, the only thing you can do is the proportional allocation. Okay. So that's something you can prove. And so that's sort of an axiomatic justification of why you do proportional allocation in something like a proof of work or proof of stake blockchain the way we do it today. You could, if you wanted, do it in other ways, but you would then suffer from either Sybil attacks or collusive attacks. Okay. Similarly, the all pay format, and this isn't so much of a theorem, it's just like, if you're using this sort of proof of X approach to civil resistance, I don't know exactly how you get away from the all pay model. It seems, again, kind of baked in to the ways we know how to do civil resistance in layer one blockchain protocols. Okay? So their proportional allocation was less a design choice and more an inevitable consequence of other design choices. The second two examples, I think it's not crazy to consider designs that were not proportional. I'm not sure I think it's a good idea, but I don't think it's obviously crazy to consider things other than proportional. Okay. So in the next two examples, really the proportional allocation, the Tullock contest format is being suggested with intuition that it's better than the other things you could do. The assertion is not that there's nothing else you could do. It's kind of what the assertion is in the first two examples. It's that it's better than anything else you could do. Yeah. And we don't have theory to actually make that precise. It's kind of like a lot of the big open questions coming out of this talk. Right? Is it true, first of all? And can you make it precise? For example, why not do winner take all, right? Like we see this, right? Like in PBS auctions, right? It is winner take all, right? So bidders bid, the highest bidder wins. They get it. You don't run a lottery amongst them according to their bids. You decide one bidder at random. You could, you don't. Okay. When should we do one? When should we do the other? Right? And in the two examples, I'll show you the intuition for why do proportional allocation rather than like those winner take all PBS auctions. It says somehow fairer, better for decentralization, better for censorship, a bunch of things where I get the intuition, but there aren't definitions really of what we mean, let alone kind of theorems around it. Right? And so that your theoretician like me, that's a call on us, right? I would like some theory that either backs up or refutes the sort of stories people are currently telling around the goodness of proportional allocation. Okay. So we talk about those last two examples. So I'll do one at layer one and one at layer two. Okay, so layer one. So this is just about allocation of the conversation surrounding Ethereum block space, Ethereum layer one block space. How should we do that? And there's, I should say these last two examples are changing constantly. It's possible I'm about like 6 weeks out of date on these two. Okay, but still, it'll give you the sense of the kind of discussions that are going on right now. Okay. So layer one Ethereum block space. So how should we allocate? So there's been various proposals, like you could have a tester proposer separation. That's one name things go by. Execution tickets is sort of another version. This comes from the research post of Justin Drake, who's been kind of the leader in this idea. So let me just give you a second to read that. And then I mentioned that Mike and Pranav and I wrote a research post related to this talk a bit. So here's how we describe the execution tickets idea. We go through a bunch of different designs for allocating Ethereum block space, summarize, sort of try to distill them to the essence. Here was our attempt with execution tickets. The block building and proposing rights are sold directly through tickets issued by the protocol. Tickets are randomly sampled to become block builders with a fixed look ahead. The ticket has the authority to produce a block in this last slide. And I guess not written here, but important is that the tickets are non-refundable. So again, you should think about this as being kind of earned revenue. They're given back to the protocol. This is, you might recall, if you recall that paragraph from 1975, Tullock's paper, this is like literally exactly what Tullock said. Yeah, he was thinking about some made up story about like a plaintiff and defendant in the court, like, I don't know, investigating lawyers or something like this, but it's literally exactly the same mathematical. Okay. So this is the Tullock contest. You've got the proportional allocation because you randomly sample a ticket, and then non-refundable because this all pay care. So execution tickets is really saying, let's allocate Ethereum block space via a Tullock contest. I think that is a reasonably first order accurate thing to say. It's not about layer one. Let's talk about layer two. Let's talk about sequencing transactions in layer two. Specifically, why not talk about shared sequencing? So this is the idea that you might want sort of have one sequencer responsible for sequencing transactions from multiple different rollups at the same time. Why would you want to do that? Maybe you have interoperability, maybe sort of you have the super additive effects of MEV across sort of multiple rollups, whatever. Various proposals for doing this. I'm just going to single out espresso as one of the approaches toward this. So here's kind of the high level idea of the espresso market design. So the idea is that sequencers bid for the privilege of sequencing one or more rollups. So it's actually sort of has a flavor of combinatorial auctions rather than a single item auction, but let's sort of ignore that complication for now. Okay. Imagine there were 10 rollups and you were just auctioning the rights to sequence all 10 of the rollups. Think of it that way for now. And then they go on to sort of say, we could do winner take all, but we're not going to. And that's sort of this part of the post, lottery to prevent monopolization. right? So this is sort of the winner take all option. They describe a version of this first, and then they say, no, we're going to do this lottery idea instead. We're going to do proportional allocation by having these tickets and doing this sort of a random ticket winner will be chosen to actually do the sequencing over some period of time, maybe an hour, maybe a day, whatever. So again, exact same reasons, right? If you're doing the tickets idea and randomly something a ticket, that's a proportional allocation. And here again, tickets are non-refundable. So this is an all-pay structure. Okay. So these again are two setups where I think it's not crazy to think about doing something different, but it's a deliberate design decision to, again, not under these words, but one could say just use a Tullock concept. So a little bit about that. Because again, it's not like we never do winner take all options, right? Like the PBS auction is winner take all, and somehow, I don't know, I've never heard anyone say maybe we should do proportional instead. So it's worth thinking about proportional allocation versus everything else you might do, but in particular, a natural challenger would be winner take all. Okay. So why not let people buy their tickets and the person with the most tickets just wins? Yes, to sequence the 10 rolls for the next hour. Like, why not just give it to them? You could have a version where the tickets are non-refundable. That would be like an all-pay single item auction, or maybe it could even be refundable if you don't. That would be just like a normal first price auction, like a PBS auction. There's some obvious problems, right? I mean, I think a lot of it's just sort of for someone, say for like shared sequencing, it makes them nervous, sort of somewhere deep down. Like, okay, maybe in shared sequencing, but at least have kind of like specialists in these 3 rollups and specialists in these other 7 rollups. But still, like, you have like a monopoly for a long period of time, just one sequencer. It makes us nervous. And start thinking about maybe just censorship. It would be like live failures. It's all this stuff. And those are all true. But what's just important to remember is, if you do try to improve on those dimensions by switching to proportional allocation by the Tullock contest, you will lose on other dimensions, right? Which I don't think is always that much discussed, right? So really, it's going to be this tricky trade-off. So let me talk more about that. So like, if you decided to do a Tullock contest instead of a more obvious winner-take-all approach, what are some of the things you would lose that you have to take into account? Well, in general, at least if you just sort of look locally at the participants in these auctions, the welfare will drop. Okay. Maximizing welfare, if one person values the thing a lot more than others, you maximize the welfare by just giving it to them, okay? Not by splitting it up and giving pieces to people who value it less. Okay? That's simply a loss in welfare in this model. Okay. So that's one thing that might bother you. Generally speaking, the revenue is going to drop as well. In some sense, what's going on here is by moving from winner take all to proportional, you make things less competitive. Okay. You can sort of, to some extent, win in this auction, even while having lower value than you could otherwise in winner take all. Okay, so it's less competitive. If you think about the way Meyerson's lemma works, so calculating payments from an allocation pool, the auction is less competitive, it's also going to mean lower revenues. Okay. Now, we may or may not care about revenues per se, okay? But one thing that's really interesting about these last 2 examples is even if we're not trying to make money per se, the goal, right, you can still interpret revenue coming out of this mechanism as an approximation of what I call an MEV oracle. Okay? So MEV just means like what actually is the value of this block production opportunity. And so one heuristic you could use if you don't know that, you say, well, let's look at what people paid for the privilege of the block production opportunity. And if you assume individual rationality, that gives you a lower bound on the value, a lower bound on the MEV. Why would you care, right? Why would you want an MEV oracle? Well, it depends. Like in the layer 1 example, execution tickets example, there you may or may not want it. But if you want it, you do want it if you want to have something like the MEV burn idea. If you want to take MEV and have it, rather than go to the validators, go instead to the protocol or to the holders of ETH, that would require the protocol being aware of the amount of MEV, so the revenue from an auction can serve as an in-protocol estimate of that MEV. In the shared sequencing example, the layer 2 example actually becomes quite crucial that you have an accurate MEV oracle, because that's literally part of the proposed business model. Where the shared sequencer is going to be extracting some amount of MEV, but also returning sort of the fair share of MEV back to all the rules that it's sequencing. So I don't even know how you solve that problem without a semi-accurate MEV oracle. Okay. So summarizing, if you move from winner take all to proportional to Tullock contest, one of the drawbacks you have to accept is that your MEV oracle would be less accurate. Your lower bound would be a looser lower bound on the actual value of the block production opportunity. And that could be a non-trivial cost. I will say I will give you one good theorem, right? So with Pranav and Mike, we can bound how much worse the MEV oracle is relative to winner take all. Turns out to be a factor 2, which is also tight. You can also parameterize this bound in terms of the gamma and theta that I showed you. Okay. Open questions. So the obvious open question is there seems to be a lot of interest in Tullock contests. And now less so earlier because they were inevitable. Now more because they're striking people as some kind of sweet spot between multiple criteria. We have no theory to justify that intuition, or maybe even I would just say hope would be a better word. Okay. For example, there's a lot of different ways you could approach this problem. And this is not a conjecture, but to give you the spirit of what I have in mind, maybe you could show something like, if you want to be Sybil proof, okay, and you want to guarantee the existence of pure equilibrium, then maybe the maximally fair thing you can do is Tullock contest. I have no idea. But if you can prove a statement like this, that's what I mean by theoretical backing of the choice to use a Tullock contest over something else. Okay. Now to solve this, like you need a metric to even talk about this. Optimally fair. What does that even mean, right? And so in general, when you think about different ways of allocating, say, block space or anything else, what does it mean to be pro-decentralization or fair or whatever? Like presumably on one extreme is winner take all. Presumably on the other extreme is just give stuff away randomly. Maybe the Tullock contest is a sweet spot in the middle. Well, again, we don't even know that. We don't even have the definitions to really talk sensibly about that question. Okay. Even back to the foundations of Tullock contest, obviously there's some sort of unsatisfying deficiencies. Most of the literature and all of this talk has just been about the full information setting, where those utility functions are common knowledge to all the participants. How about a Bayes-Nash equilibrium analysis, where there's uncertainty over people's utility functions? There's a little bit of literature on this, but it's honestly in a pretty unsatisfying state at the moment. Another way you could extend the basic theory is what if you didn't just have one item, what if you had many, which is actually then directly relevant to that shared sequencing problem that I discussed. I think I'm over time, so let me stop there. Thanks a lot.
Thank you. I think we have time for one question.
So, like Max Bitcoin paper, they assume like constant rewards, and then you assume roughly constant rewards, and then they do heterogeneous costs, and you do heterogeneous operation costs. So, where exactly is the difference in the model that makes the difference?
Yeah, I forgot to say this. So the way I talked about the Arnasty-Weinberg model, it sounded slightly outside the Tullock contest model because you had heterogeneity in cost. So that would be like instead of minus BI, you have minus BI times CI, where CI is kind of the hash rate. You can it's sort of the dollars per hash rate or something like that. But you can just scale it, right? So the point is, because all that stuff is linear, heterogeneity in the cost just maps back to heterogeneity in values. So actually, they map totally to a Tullock contest as well. And then it's the same. Like the mathematical model is the same in their paper and ours. We just had different interests, so we proved different theorems.
So you can still prove some roughly, like your style results in Max paper as well. Like
I mean, from a mathematical perspective, both our papers are literally just like, here are some properties of. So for our paper, it's one section out of a bunch, right? But that section of our paper and their paper is really just like, here are some properties of pure Nash equilibrium and Tullock contests. Like on a math level, that's what the results are. Our interpretation. Okay. Thanks again.